So today we're going to finish up lecture set number 5, and then we're going to start lecture set number 6. So lecture set number 5 was devoted to cluster sampling and two-stage cluster sampling. We started off by introducing cluster sampling, and then we looked at some of the basic or traditional estimates that we have seen throughout the course. So we talked about estimating the mean, the total, the proportion. We talked about how to address situations where you were missing information. So in particular, we looked at how we could still estimate a population mean or total when we did not have the true number of elements across the entire population, which we designated capital M. Following that, we talked about a situation where if you have the same number of elements within each of the clusters, you can effectively use ANOVA style calculations to find the variance of your estimator. And you can also use these calculations to find an approximation to the variance of the simple random sample estimator. And then you can compare the two in terms of their relative efficiency. After this, we started talking about two-stage cluster sampling. Two-stage cluster sampling is a it's a pretty similar idea. So effectively, you randomly sample the number of clusters, and then within each of the clusters, you randomly sample the number of observations. So within two-stage cluster sampling, again, what we focused on was basically estimating the mean, the total, and the proportion, and that's what we spent the majority of Wednesday doing. Today, we're going to finish off with just a little bit of a discussion on how we can expect the two-stage cluster sampling approach to behave when we have an equal number of observations across each of the clusters. And then following that, we'll start lecture set number 6. And lecture set number 6 actually starts the last unit of the course, which is really sort of a survey of different topics within the sampling study. So what I mean is, up until this point, we've basically studied a different sampling strategy across the second, third, and fourth and fifth lecture set, right? So we had simple random sampling, and then we had systematic sampling within the simple random sampling unit. And then we had stratified sampling, and then we talked about ratio estimation. So actually in that situation, we didn't study a different sampling strategy, but we talked about a different estimation approach within stratification and within simple random sampling. And then we started talking about cluster sampling. So the last few units of the course will be sort of shorter lecture sets that talk about a variety of different ideas. And in lecture set 6, as we'll see today, we're going to talk about basically how you treat samples where the probability of selection for each of the units is not equal. And this is unique to what we have seen so far, because up until this point, we've assumed every unit in the population has the same probability of being selected. So with that being said, we're going to start off right near the end of lecture set 6, as I've noted here. Just a reminder that Q3 is on Monday, March 29th. So students have started to email regarding their preference or their preference in for accommodation and whatnot. So again, if you can let me know sooner rather than later what you would prefer in terms of the lecture quiz, that would be great. And then we have the final assignment, which is due April 9th, and that's, I believe, 2 weeks from today. And that final assignment, you have everything that you need to complete that at this point. Even the material that we're covering today, the material we're covering today, I don't believe is actually tested on assignment 5, though I could be wrong. So by the end of lecture set number 5, you will certainly have everything you need, but I'm pretty sure that at the end of the class Wednesday, you actually had all the material needed for that. So lots of time to finish that up. And as always, if you have any questions, please let me know. Okay, so the last situation. So again, what we're going to talk about here is just effectively a special case of two-stage cluster sampling. where we have an equal number of observations within each of the clusters. So in this case, we're just saying that little m is equal to little m1 is equal to little m2 is equal to little nm, mn for all n clusters that we have collected. Again, little n represents the number of sampled clusters. Under this condition, we can show that the estimator for the mean, or for the population mean, is equal to 1 over n times m multiplied by the double sum of the yij. So this is just saying that the estimator of the mu is simply the average across all clusters and all observations within each of the samples, okay? Which makes sense because this is the form we've been using before anyways. Okay, so to estimate the variance, we can use kind of ANOVA type calculations when we have this equal, when we have an equal number of observations across each of the clusters. Okay, so our estimate for the variance of mu double tilde DCS is given by 1 minus F1 multiplied by the mean squared between over n minus m plus 1 minus F2 multiplied by 1 over capital N times the mean squared within multiplied by little m. Okay, and you can see here that F1 is equal to n over n and F2 is equal to little m over capital M. So we basically have here and here, we have our two sort of FPC calculations as we have seen them so far. So this would be kind of like an FPC for the number of clusters, if you will. Right. And then this would be sort of like this would be the more traditional FPC within each of the clusters for the population size. Actually, this would be the true FPC. And this would be the one that we're typically dealing with. Okay, now you can see that the mean squared between has the traditional style of formula. So we're just basically calculating the sum of the squared distance of each cluster mean to the overall mean. And this is what you would expect when you're considering a mean squared between measurement, because it's looking at the differences between the averages of each of the clusters. And then our mean squared within, again, this is effectively what we would expect. This is just an approximation to the variance of each observation around their respective cluster mean. So you can see here that we have the yij minus the mu hat I. This is basically just taking the square difference between the observation in cluster I with respect to its mean. And you can see that we get a nice simplification here, and we can show that MSW is equal to 1 over n multiplied by the sum from I equals 1 to little n of sigma hat I squared, where sigma hat I squared would be the traditional estimator of the variance for each of the clusters. I think actually, sorry, this should be the n, and this should be the m. That makes more sense. All right. Okay, so from equation 19, so from this approximation to the variance, we can actually make a few interesting notes. First off, we can say that when capital N is large, so when the number of clusters are large, the variance of, or the estimate for the variance of our two-stage estimator when m is equal to the mean squared between divided by nm. So it only depends on the cluster means. If little m is equal to capital M bar, or F2 is equal to 1, then two-stage cluster sampling reduces to individual cluster sampling, right? So what we can see based off of those first two approaches is effectively, if capital N is very large, it's saying that the second term here, so this term, goes to 0 in that case. So therefore, we have the reduction mentioned on the previous slide, or on the preceding slide. And then in the second point, what they're saying is basically, if F2 is equal to 1, so again, in the second term, again, this term goes to 0, and you have the same conclusion. So effectively, the variance of mu double tilde DCS is only equal to the value in the first term of expression 19, when that actually is the term for cluster sampling, or the variance for a cluster sampling approach. If little n is equal to capital N, then we have kind of the opposite effect. So the variance of mu double tilde DCS is equal to 1 minus F2 multiplied by the mean squared within divided by n over m. And this is an approximation to the variance from stratified random sampling. So in general, what we can say is that when little m is close to capital M, so when the number of observations in each cluster is close to the true number of observations, two-stage cluster sampling behaves like cluster sampling. And when little n is close to capital N, so when the number of selected clusters is close to the true number of clusters, two-stage cluster sampling behaves like stratified random sampling. So from this, we can say that if the clusters are heterogeneous within, so if the clusters are very different within, we should use cluster sampling. And if the clusters are very similar within, then we should stratify. So again, what we're doing here is we're just looking at a special case of the two-stage cluster sampling approach where we have an equal number of observations within each of the clusters. In the situation where we have an equal number of observations within each of the clusters, we have an approximation to the variance that would be based off of ANOVA type calculations. And in that situation, we can show the relationship between two-stage cluster sampling and cluster sampling, and between two-stage cluster sampling and stratified random sampling. Any questions? All right, so we're going to wrap up with a pretty simple illustration of these two formula. This is a direct application of the formula given on the previous slide. So we're only considering this for just for illustration purposes. In part C, I have calculate M if the costs are equivalent. So I'm just going to show you how this would work. We didn't talk much about the derivation of this formula, but I'll explain to you what the formula is, give you a little bit of insight into where it comes from, but more or less just kind of show you how we can compute the number of elements per clusters when we assume that cost is equivalent. All right, so in part A, we have the following. A bottling service is being tested by a company. From 24 cases of 12, 5 cases of and 4 beers per case are randomly selected. Okay, so we have capital N is equal to 24. We have little n is equal to 5. Okay, and then we would have capital M1 is equal to 12. Well, actually, we would have capital M1 to capital MN is equal to 12 because we have 12 bottles per case. And then we would have little m1 to little m5 is equal to 4. Right? So we have 24 potential clusters, if you will, which are the cases of beer, the cases of beer. We have little n is equal to 5 selected cases of beer, so that's the number of clusters. Per case of beer, we have 12 total bottles, but from each of the selected cases, we only take 4 bottles, hence the declarations given below. So if we wanted to find capital M, that would just be 12 times 24. Right? So whatever that would work out to be. And then little m would be equal to 4 times 5, which is 20. So 20 total bottles across the entire experiment. And then 12 times 12 is 144 times 2 is 288. I think that's correct. Anybody want to? Nice. Okay, so you can see that for each case of beer, we are given the mean or the average amount of fill per bottle. Okay, so here we have average amount of fill. And then here we have variance of amount of fill. All right, in part A, we want to estimate the average fill per bottle. So we want to estimate the mean amount of fill per bottle for the entire population. Okay, so in this case, we're going to use the formula that we gave above. So mu double tilde DCS. Again, just for clarity, so you can, from the description given above, we can see that this is a two-stage cluster sampling approach, but we have equal number of observations per cluster. So that's why we can use the formulas that we just described. It's a situational application. So the formulas that we just gave are only valid in the context or in the case that we're using the two-stage cluster sampling approach. All right, so I have it written as 1 over n times m. Well, I guess we have two ways that we can write this. Given the situation, we don't have the raw data, so we can just take the average of the averages from each cluster. Right, so this is going to be 1 over 5 multiplied by 7.9 plus 8.0 plus 8.0 plus 7.9 plus 8.1, which is equal to 7.98. Right, in part B, we want to place a bound on the error of estimation if the mean square between is 0.028 and the mean squared within is 0.026. Okay, so we're going to have variance of mu tilde DCS is equal to 1 minus F1 multiplied by the mean squared between over n times m plus 1 minus F2 multiplied by 1 over capital N mean squared within divided by little m. All right, so let's try to get myself a little more room here. Okay, so F1 is going to be little n over capital N. So we're going to have 1 minus 5 over 12 multiplied by the mean squared between, which is 0.028, divided by the total number of clusters, which is 5, multiplied by the total number of observations, which is 20, plus 1 minus, and then we have little m over capital M. So that's going to be 20 divided by 288. Right. I'm just gonna make sure. Should be fine. Multiplied by 0.026 divided by 20 again. Oh, sorry. Okay. And then I forgot. term here. It's actually a 24. And then this is going to be 1 over 24. Yeah, F1 is little n over capital N. Yeah, 5 over 24. All right. Okay, I'm just going to check this to see. Those are pretty different. Okay. All right. I think I just made a bit of a mistake with my language here. I mean, that would be. All right. So I misinterpreted one thing here where I took the total as capital M and I took the little m as being the total across all of the clusters. Actually, it's fine. I'm just going to leave it. Yeah, no. Okay. Sorry about this. So okay, I'm just going to make a small change here because this is supposed to be the M's are supposed to be interpreted slightly in a different way than how I have them written. So I'm just going to explain the change and then I'll show you the adaptation. So in this formula, so I'll start back on this slide. So you can see that on a few occasions here, for example, if you look on slide 38, you have samples of size M from within each cluster. So we're actually taking little m to be the number of observations per cluster rather than the total across all the clusters. So I'm going to just make the following notes. I'm going to put an mi here just so we can keep the same definition. So it's going to be mi from within each cluster. And then we would also have mi here. Okay. So this way, at least what we can show is that and then this actually would have to come inside. Yeah. Anyways, the point is that little m is supposed to represent the number of values per cluster. So in this case, it's supposed to be the number of bottles selected for each of the different cases, which would be 4. So we're gonna actually, I guess we'll just have to come up with a different notation for the total. That'll probably be easier than changing all this other stuff. Okay, so the little m is gonna represent the number of observations per cluster. So the point is that this value here and this value here, this is gonna be capital M and this is gonna be little m in this context. And then we can call this value like m, I guess we can call it mt and little mt, just so that it's clear the differences. So little mt would be like the total number of observations across the whole experiment. And then capital MT would be the total number of bottles across all the cases. And little mt would be the total number of bottles across all of the sampled cases. And this, at least this way, we just don't get it as mixed up. And okay, so now this is going to be a 4 representing the number of observations per cluster. And then F2, which is going to be little m over capital M, this becomes 4 over 12. All right, there we go. And then here we're going to have a 4. Sorry about that. I just got a little bit ahead of myself. Okay, so we have little m representing the number of bottles per case, capital M representing the total number of bottles per case, and then we'll let capital MT be the total number of bottles in the entire experiment, little mt be the total number of bottles across the sampled cases. All right, so then our variance estimate is going to be 0.00128, and then our bound is going to be 1.96 multiplied by the square root of 0.00128, and this is going to be 0.0718. Therefore, the 95% CI for mu will be 7.98 plus or minus 0.0718. Okay. Okay, and now in part C, we want to calculate the number of observations per cluster, so little m, given that cost is equivalent. So to do this, we can show the following. To calculate, well, we can use the following, I should say. To calculate little m, which is number of observations per cluster, given cost is the same, we can use little m is equal to the square root of sigma squared w divided by, well, hold on a second. Sigma squared w divided by sigma squared b. Okay, and here we have sigma squared w is equal to MSW and sigma squared b is equal to 1 m MSB minus MSW. It's a comma. There we go. Okay. All right. So in this case, we would have, therefore, m is equal to the square root of 0.026 divided by 1 over multiplied by 0.028 minus 0.026 . And then this should give us something in the area of the square root of 0.026 divided by 0.001, which is equal to 7.211. Okay. So take 8 observations per cluster. Yes, thank you. All right, got there slowly, as per usual with this stuff. All right, yeah, so again, apologies for that. Just the mistake that I made is I took little m to mean the total number of observations across the entire, all of the selected clusters, but it's in this context, the number of observations per cluster. So with that being cleared up, then we have little m being 4, the number of selected cluster, or little m being 4, the number of bottles per cluster, little n being 5, which is the number of selected clusters, capital N is 24, the total number of cases in the population, and little n is 4, which is the total, which is the number of selected cases from the 24 that were available. Yeah, little n is 5 from the total that's available. Okay. And then this last part in C here, so the calculation where cost is the same. Just I should clarify here that when I say cost is the same, what I mean is just well, I'll just explain it. But when I say cost is the same, what I mean is that the cost associated with collecting like the cluster and the cost associated with collecting the observation within the cluster is equivalent. So that's what I mean by it being the same. Okay, so cost of selecting each cluster and observation within the cluster is the same. No, not in these calculations. Because I just wrote them as capital M subscript T and little m subscript T just to specify that they are different from the capital M and the little m. So that was the purpose of this introducing the subscripts. Otherwise it was going to be um, why we have the 4 and the 5 below instead of the 288 and the 20 would have been confusing. All right. Okay, any other questions? Okay, so that brings us to the end of lecture set 5. Got there after all. So that again concludes the cluster sampling lecture set. And it also brings us to the end of our study of different sampling strategies. So we've seen simple random sampling, systematic sampling, stratified sampling, cluster sampling, and two-stage cluster sampling. So we've seen 5 different strategies for collecting observations from a population. In each of the cases, we've basically focused on the same thing, which is estimation of the mean, estimation of the total, estimation of a proportion. We've talked a lot about the properties of the estimators. So we've derived the variance approximations. We've shown that the estimators are unbiased. And then we've looked at different topics within each of those units. So for example, with cluster sampling and two-stage cluster sampling, we've talked about how the estimates can be adapted or changed in the case that we have equal cluster size. In all of the different cases, we've talked about sample size calculation, for example. In the systematic case, we talked about relationships between the systematic estimators and the simple random sampling estimators. So we've had all these different sort of like branches coming off the main tree, which is just the study of the individual sampling strategy. So now what we're going to start to do is look again at, or as I mentioned before, is we're going to look at different topics within the sampling scheme. So we're going to talk about a variety of different situations and different calculations that we can make depending on what it is that we're interested in. The first of these sort of unique one-off topics is how our estimators adapt when we no longer have equal selection probabilities for the units within our population. So up until this point, we have assumed that the probability of collecting each unit is the same. And this was the underlying basis for our simple random sampling approach, where we gave every observation the same chance of being included in the sample. But we might be in a situation where we have a population that has some number of units and the probabilities of selection for each of those units is not equivalent. So we're going to look at how our estimates for, say, the mean and the total, the traditional estimates that we've talked about throughout the class, adapt or change rather when we don't have those equal selection probabilities. Okay, so just as a reminder, we've been focused on probability sampling. At the very beginning of the course, we talked about different types of sampling strategies, but we've utilized the probabilistic approaches because those approaches give us, let's say, the best chance at collecting a representative sample from the population that we are working with. We can break down the two, or probability sampling, into two very general types of strategy. So we can say that we have either probability samples where we sample with replacement, or we have probability samples where we sample without replacement. We've talked about the idea of sampling with replacement a little bit. For example, on assignment number 1, we had a question where we had to show the variance of the mean estimator for simple random sampling when we sampled with replacement. But that was pretty much the only time that this has come up, at least in terms of assignment questions. And I think that we probably talked about it a little bit just in general in the second lecture set when we introduced simple random sampling. We've looked at simple random sampling or sampling without replacement quite a bit. Almost all the strategies that we've used, we have effectively looked at it from the point of view that we have not replaced the units within the population at any point. So that would be sampling without replacement. Okay, so we're going to start off just by kind of going over how we would expect the estimators to behave, or how we would, well, yeah, we're going to just go over some basic illustrations of how, in very general cases, we would approach a sampling problem where we have replacement, and then how we would approach a sampling problem where we do not have replacement, kind of starting at the beginning, if you will. So first off, we have in this example, suppose a population consists of elements u equals 1, 2, 3, 4. So these are the population elements. And we have delta 1 equal to delta 4, which is just saying that the probability of selection for each unit in the population is exactly the same. All right, so in part A, we're being asked, what are the probabilities of observing each possible sample of size 2 when sampling without replacement? In part B, we want to compute mu hat for each sample. And then in part C, we want to determine if this estimate is unbiased. Okay, so for part A, we can lay out this information in a table. This is an easier way to do it. So we'll have here, for example, sample, and then within each sample, we're going to write out all the possible samples that we can observe. And then here we're going to have the probability associated with collecting each of those samples. All right, so well, the first sample is 1, 2, the second sample 1, 3, the third sample 1, 4, 2, 3, 2, 4, 3, 4. Okay. And then we would also have 1, 1, 2, 2. I'm gonna try something really quick here. I think there's a way to. We would have 4, 4. Okay. So we are sampling with replacement in this illustration. So that means that we can observe samples that have the same number of elements or the same element multiple times. So that's why when we look at the list of the samples here, we have what you would expect. So the sample that contains elements 1, 2, the sample that contains elements 1, 3, 1, 4, 2, 3, 2, 4, 3, 4. Those are the traditional without replacement samples. But then we also have 1, 1, 2, 2, 3, 3, 4, 4, because we can observe each of those samples as well. Okay, we're told that delta 1 equals delta 2 equals delta 3 equals delta 4. So delta 1 is probability unit 1 is selected, right? So delta I would be the probability the ith unit is selected. So if these are all equivalent and we know they have to sum to 1, we can show that each delta I is equal to 1 over 4, which is equal to 0.25. Right, so each observation has the same probability of being included in the sample. So since we're sampling with replacement, these probabilities are going to be consistent across the entire study. So the width replacement estimator is going to give the exact same probability to every unit, regardless of where it is selected. This is kind of the basis of this width replacement idea. So we're going to have this same value being repeated across the entire experiment. Oh, wait. Of course, I mangled that as per usual. Okay, sorry. Brutal. All right, so that explanation that I just gave is true for the last 4 cases. So we're gonna have the same probability of selection being associated with each of these samples here. 1, 1, 2, 2, 3, 3, 4, 4. For the sample 1, 2, there's actually 2 different ways that we can observe this sample. So we can collect observation 1, then observation 2, or we can collect observation 2 and then observation 1. So this is going to be 2 times this. There we go, which is 1/8. Okay. So the 2 here is since you can pull 1, 2 or 2, 1. So it represents the fact that we can have 2 different samples with the same elements, but they can be observed in a different order. Okay, and now this probability would be consistent across the first 6 listed samples. All right, there we go. And then we should be able to show, so that would be 6/8 plus 4/16. Yeah. Okay, that makes more sense too, because otherwise it would have added to 10/16, but all the probabilities must sum to 1. And you can easily show now that you have 6 times 1/8, which is 6/8, plus 4 times 1/16, which is 4/16. 6/8 is equivalent to 12/16. 12/16 plus 4/16 is 1. So that works out. Okay, so here then we would also have the sum of the PS is equal to 1, but I just don't have the room to fit that in. Okay, well, I guess that'll probably be the end for today. But so on Wednesday, we'll continue with this example. So we're gonna show how we can estimate mu for each of these different samples. We've seen this illustration before, so we'll just go over it again kind of quickly. And then we'll show how we can use this approach to show that the estimate is unbiased. This is almost actually from an empirical point of view. And then we're going to look at the exact same situation, but when we sample without replacement, and we'll see how that changes the probability of selection for each of the samples. Okay, so again, on Monday, we're going to have quiz number 3, which is the last quiz. Quiz number 3 covers post-stratification through lecture set 4. So that's, I wrote the exact slide numbers in an announcement, but it's post-stratification from lecture set 3 to the end of lecture set 3. So that's post-stratification double sampling, and then everything in lecture set 4. And then that'll be held in the usual way. So the in-class or in-person offerings of the quiz. And then we'll have class on Wednesday. And then I was told yesterday that next Friday is actually a holiday. So I guess we'll just have the 1 lecture next week. But if you guys need accommodation, please let me know. If you have any questions, please let me know. And I have office hours after this class if you have any questions at that point as well. So have a good weekend. And I will see you, some of you, on Monday.